Hello, this video is for you if you found the previous one on proofs by induction with divisibility a bit cumbersome or difficult, or at least just you want to look for another method. So please have a pen and paper with you. I'm going to go through 3 examples, so it's a bit longer than the other videos, so pause, work through each example, make sure you know what you're up to at each stage. Also, I'm going to assume here you know how to do step 1 for each proof, and that you can write out the beginning of step 2, prove true for n equals k plus 1, if true for n equals k. So here's an example. 7 divides into 10 to the n minus 3 to the n for all n. That's what we want to prove. So in step 2, we will want to prove that 7 divides into 10 to the k plus 1 minus 3 to the k plus 1, what we get by plugging k plus 1 in instead of n there, on the assumption that when we plug k in instead of n there, this is true. And the way we do here is we build up from this to this, rather than going the other way around. So here we say, right, 7 divides into this. Right. If 7 divides into that, 7 divides into 10 times it too. So 10 times 10 to the k is 10 to the k plus 1 times, and you've got minus 10 times 3 to the k. Okay, this looks near telling us something about that. It will if we just do this simple thing. Take away 3 to the k plus 1 and then add a 3 to the k plus 1. And we've still got our minus 10 times 3 to the k. Okay, so all we've done is we've put in a minus 10 to the 3k plus 1 and a plus 3 to the k plus 1, which balance each other out. When we've done that, we can collect our terms. And we've got here the thing that we want, 10 to the k plus 1 minus 3 to the k plus 1. And here we've got 3 times 3 to the k minus 10 times 3 to the k. And 3 minus 10 is minus 7. So this is minus 7 times 3 to the k. Okay, but that's divisible by 7. So if all this is divisible by 7, and that bit is, this bit must be 2. So 7 divides exactly into 10 to the k plus 1 minus 3 to the k plus 1, which is exactly what we wanted to prove. Right, another example. And we will take here, we're going to prove that 13 divides into 10 to the 2n minus 1 plus 3 to the 2n minus 1 for all n. Okay, again, assume you've done step 1, you've done the beginning of step 2, you know what you've got to prove. In step 2, you've got to prove that 13 divides this with k plus 1 plugged in instead of n, which is 10 to the 2k plus 1 plus 3 to the 2k plus 1. And what we've got to work from is, suppose for the sake of argument that it's true for n equals k, which means you plug k in there instead of n, and you get 10 to the 2k minus 1 plus 3 to the 2k minus 1. Okay, we want to get from there to there. Right, okay, 13 divides into that, then 13 certainly divides into 100 times that, that's 10 squared times that. 10 squared times that is 10 to the 2k plus 1. And we've just got 100 times 3 to the 2k minus 1 there. Okay, same trick again. We're going to put in a bit to make this like that, and then balance it out. Right, so that's okay because we've just added something and taken it away. Then we can collect those terms. We've got 10 to the 2k plus 1 plus 3 to the 2k plus 1. That's all that bit. What have we got here? We've got minus 9. That's minus 3 squared times 2 to the k minus 1. Because 3 to the 2k plus 1 is 3 squared times 2 to the k minus 1. So we've got minus 9 plus 100, that's plus 91. Right, okay. However, at this point, we know 13 goes into that because 13 goes into 91. So if 13 goes into all that, then it must go into that bit too. So 13 goes into that, which finishes our step 2. Third example coming up. Right. This one is going to be a claim that 13 divides into 14 to the n plus 26n plus 12 for all n. And you see there's a slight twist here. Right, we know what we want to prove in step 2. We want to prove that 13 divides this with k plus 1, put in instead. Right, and what we have to work with is, suppose for the sake of argument, that it's true for n equals k. And that implies that 13 divides 14 to the k plus 26k plus 12. I've just plugged k into that. Okay, now, with this one, and right, this is a bit of a weird rule of thumb, but if you get something with only one number raised to a power of n, this will work. I'm going to do something simpler than multiplying this. I'm just going to add to this something that 13 obviously divides into, which is 13 times 14 to the k. Yeah, 13 obviously divides into that. Okay. Right, so I've got 13 to the k plus 13, 14 to the k's. How many 14 to the k's is that? That's 14 of them. So 13 divides into 14 to the k plus 1, that makes, which is what we wanted to get, plus 26k plus 12. Okay, we're almost there. What's missing? Oh, 26. Well, you can add 26 because 13 goes into 26. You can just do that. And we're done. Right. Good. One more example. This one I'm going to prove that 3 divides n cubed minus n for all n. Again, I'm going to assume that you're good with step 1, you're good with the first line of step 2, which says prove true for n equals k plus 1, if true for n equals k. And what we do here then is we want to prove that 3 divides k plus 1 cubed minus k. And what we have to go on is that this is true for n equals k. This is supposed for the sake of argument, and that tells us 3 divides k cubed minus k. Now again, I'm going to mess around with this to tell us something about that by adding. So 3 divides k cubed minus k, it will certainly divide that, won't it? Because all I've added are things which 3 goes into. Why have I added those particular things that 3 goes into? Because this now looks pretty much like k plus 1 cubed, which you can work out using Pascal's triangle. It's, in fact, it's k plus 1 cubed, all except we'd have to add in a 1 to make it k plus 1 cubed. So what we got is k plus 1 cubed minus 1 minus k, which is minus k plus 1. Aha! That is exactly what we wanted to prove. Sorry, or it would have been if I'd written it correctly at the beginning. So, again, we can get what we wanted by adding in this case, which is simpler than multiplying. So all these are ways of doing induction proofs with divisibility, where in step 2, rather than going from the expression you've got for the k plus 1th term and then breaking it down to what you're assuming for the sake of argument about the kth term, you start with what you're supposing for the sake of argument and you mess around with that by adding or multiplying until you get what you want to prove for the k plus 1th term. So you might find that a better method. Try it.